Welcome to experiment 8. This experiment is about sequential circuits. In this experiment we will perform and demonstrate synchronous and ripple counters and one of the basic flip-flops, that is the JK flip-flop. The last experiment that we performed was of combinational circuits. The difference between a combinational and a sequential circuits are that the sequential circuits use clocks to drive its input and output conditions. So the first part of this experiment is to verify the operation of a JK flip-flop. A JK flip-flop is one of the basic flip-flops which is driven by a clock, and based on the input conditions a set of output values can be observed. The truth table for this JK flip-flop is given at the back side of the handout. Currently we will demonstrate the truth table by making the circuitry on the breadboard and verifying the output on the digital test board. The IC number 4027 is used for the JK flip-flop are embedded on the IC number 4027. The pin configuration of this IC is given in the handout. The connections are made as per the pin configuration. Currently we are demonstrating for a single JK flip-flop the truth table. Here these two switches are taken as an input to this breadboard or the JK flip-flop. The first switch is connected with the J input of this IC, and this switch is connected with the K input of this IC, and we have connected a clock from the digital test board to this IC and given a power supply from the power supply generator, that is of 5 volt. Currently this red LED is showing the clock variations, that is the positive and negative cycle of the clock. Since the output will be verified on this green LED, that is on this digital test board. Currently, since both the switch, that is J and K input are 00, as given in the truth table of the JK flip-flop, the output should be the previous output, that is Qn plus 1 is equal to Qn. Since the previous output was 0, so currently the output generated by this flip-flop is also 0. Now we will change the input condition. Say suppose I make J equal to 1 and K equal to 0. Now J is equal to 1 and K is 0. We can see that the output is 1. Now for J equal to 0 and K equal to 0, the output is again 1. That is the previous output. It means that whenever the input is 0, 0, the output always will be the same as the previous output. Now if I will make J equal to 0 and K equal to 1, the output is 0. Again if I will make both J and K equal to 0, the output is the previous output, that is 0. Now if we will make both the inputs high, that is 1, that is J and K are both 1, we can see that the LED is toggling between 0 and 1. That is for J equal to 1, K is equal to 1 condition, the output is equal to Qn bar, means it always complements the previous output. Since at this clock this is 1, now at the next clock it is 0. So it will always toggle between 1, 0, 1, 0 depending on the previous condition and on the clock pulse. Since this IC is a positive edge triggered, so whenever a positive edge of the clock comes, it toggles from 0 to 1 or from 1 to 0. Hence this verifies the truth table of this JK flip-flop. Now the second part of this experiment is to design a divide by 8 ripple down counter. The ripple down counter is an asynchronous counter because the clock given to all the flip-flops are not the same. That is, all the flip-flops are not driven by the same clock. In a ripple counter, the clock is driven by the previous flip-flop, either the output or its complement. That is, the output of one flip-flop is used as a clock to drive the second flip-flops, and so on. Either the normal output can be used as a clock, or the inverted of the output can be used as a clock. That is either Qn or Q bar. Now this since for a divide by 8 ripple down counter will have a sequence from 111 to 000 state. That is from 7 to 0 in decimal form. The number of bits required for this sequence is 3. So the number of flip-flops is given by the minimum of 2 to the power n, where n is the number of bits required to represent a sequence. Since here we require 3 bits, so the flip-flop will be, since we have 8 sequence over here, that is from 7 to 0, so the number of flip-flops will be log 2n. So the number of flip-flops for this n is the number of sequence, so the number of flip-flops required will be 3 for this ripple down counter. So there is a direct relation between the number of sequence required or the number of representation bits for a sequence and the number of flip-flops required. For example, for divide by 16 counter we would have required 4 flip-flops, since we will have 4 bits to represent a sequence. Here the counter down counts from 7 to 0, starting from all ones to all zeros. Now we have designed the divide by ripple age counter on the breadboard, as can be seen, and will verify the output on the digital test board. Again, the output will be checked using the 7-segment display. In this, since we require 3 output bits, so we have grounded the MSB, single MSB input to the ground. The rest 3 are used as to display the output of the counter generated by it, and we'll give again the power from the power supply. The output can be observed on this 7-segment display. It's decreasing from 7, 6, 5, 4, 3, 2, 1, 0, again back to 7. So this sequence will keep on repeating, hence it is called a divide by 8 ripple down counter. As explained that why it's called ripple, that the change in one flip-flop state ripples to the other flip-flop, which changes the state of the other flip-flop, and this change in state of the second flip-flop will ripple to the third flip-flop of this counter. So the effect will move from one flip-flop to the next, from next to the next of it. So that is why it's called a ripple counter. Now we are able to observe this sequence on this 7-segment display. Currently the clock can be put into auto mode as well as manual mode. Currently this is in auto mode, that is the clock is being driven automatically, or that the counter is getting the clock automatically from this digital test board, which drives the counter or the flip-flop, which generates the output. We can have a manual driven clock, we can give a manual driven clock to the flip-flops, so that we can observe the values of the counter manually also. Now I'll put it into manual mode. This switch is used to put in either auto or manual mode for the clock. Now currently I have this 7-segment is displaying 5. So, and this is used to give the it is used to give the trigger pulse to this counter. So whenever I'll press the that toggle switch, so that means that it will generate a positive pulse. It will send a positive pulse to the counter, and on each positive pulse, it should change its state. That it should decrease from 5 to 4. Since the counter or the IC is a positive edge triggered, so only for positive triggering only it will change its state. Now I will manually give a pulse to it, pulse to the counter. So the state is being changed from 5 to 4. Again I have pressed it and it's 3, displaying 3, 2, 1, 0, 7, 6, 5, 4, 3, 2, 1, 0. So we can see that manually also we can control the sequencing of this counter. That is the clock. We need not give the clock to it from directly from the digital test board. We can manually control the output of this counter by using the manual mode of this digital test board as per our convenience. The third part of this experiment is to design a divide by 8 ripple up counter. Again, since this is a ripple up counter, hence it is an asynchronous counter. That means the master clock will not be the same for all the flip-flops, and will have separate clocks as separate clocks for each of the flip-flops. The one of the flip-flop output will act as a clock for the second flip-flop, and again and so forth for the other flip-flops. In this, the clock for the second flip-flop will be the inverted or the complement output of the previous flip-flop for this ripple up counter. Since this is a divide by 8 ripple up counter, so it will count from 0 to 7. It will increment by 1 from 0 to 7. The previous one, it was a down counter which decremented the value from 7 to 0 by decrementing 1 from the previous count. In this, it will increment by 1, that it will count from 0, 1, 2, 3, 4, 5, 6, 7, again back to 0. Hence total number of states is 8, and number of bits to represent this values will be 3. Hence the number of flip-flops required will be 3. So we'll have the states from 0, 0 to 1, 1, 1 state. The inputs given to all the flip-flops J and K are 1, and the clock as explained that it will be the first LSB flip-flop will have clock from the digital test board, and the next flip-flop will have the clock from the complement output of the previous flip-flop. Hence we have designed this divide by 8 ripple up counter on this breadboard, and will again observe the values or the count values on the digital test board on this hexadecimal display. Again, since we require only 3 bits to display the output of the counter, so we have grounded the 4th pin, that is the MSB of this hexadecimal input, and we will give the output of the counter to these 3 pins of this hexadecimal input. So these 3 inputs will again drive this 7-segment display, and we can observe the count values of this counter on this 7-segment display. Again, the power given to this circuit will be from the power supply. So we can see that as I have given the power supply, we can see that the counter is generating from 0 to 7, and it's keeping on incrementing by 1 up to 7. 0, 1, 2, 3, 4, 5, 6, 7, and again back to 0. So this sequence will be keep on repeating. At each clock pulse, there will be a positive edge of the clock. There will be an increment in this value. Again, as explained earlier, we can have a manual triggering for this to observe it. So we can see that the truth table or the design table for this divide by 8 triple counter is verified on this digital test board. Hence the observation is coming out to be correct. Now the fourth part of this experiment is to implement a 3 divide by 3 synchronous up counter. A counter is basically a circuit designed by flip-flops which generates a given sequence in a pattern or in an order. And why this circuit is called as synchronous counter? Because the clock given to each of the flip-flops are the same. That is, the master clock for each of the flip-flop is the same. So the clock at each flip-flops is the same. So they will toggle together, or whatever the output will be there, they will have the same effect for the clock, because the clock given to them will be the same. Currently, as given in the handout, the divide by 3 synchronous up counter will have a sequence from 00 to 10. That is 00, 01, 10. In decimal 0, 1, 2. The 3 decimal state that is 1, 1 will not be used in this synchronous up counter. So the truth table for this, or the sample table for this synchronous divide by 3 counter is given in the handout. In this, the 1, 1 state is unused and the rest 3 states are implemented. So as given in the handout, we have designed the divide by 3 synchronous up counter in the breadboard and will verify this on the digital test board. The output, the counter output will observe on this 7-segment display. Currently, the output generated by this counter is 00, so its output is 0. So when the output can be observed when this will show from 0, 1, 2, and from 2 it will again go back to 0. It will not go to 3. So we can observe the counter wave output on this 7-segment display. We can see that by the connections we have made on the test board, breadboard, and as given in the pin configuration of this 4027 IC, we have made this connection of the counter, and we are giving the output of this counter of the 2 flip-flops to this the inputs of the 7-segment displays. This one is the MSB, this MSB, this bottom one is the LSB. Since we need only 2 bits for this counter, so we have grounded this MSB and the second most MSB of this hexadecimal input to the ground, and the rest two we have connected with the output of the counters. So depending on the output generated by the counter, the output is observed on this 7-segment display. So depending on the output generated like 00, 01, 10, we are getting the output, and it is displayed on this 7-segment display in decimal form. So we can see that the counter doesn't go to 1 state, that is the decimal 3 state. It continuously counts to, keeps on repeating the sequence 0, 1, 2, 0, 1, 2, 0, 1, 2. Hence this counter basically counts, or it, so that is why it is called a divide by 3 up counter, because it is counting, incrementing the value by 1. So it's a up counter, and it's keeping on keeps on repeating the same value 0, 1, 2, 0, 1, 2. Hence it's a counter that keeps on repeating a particular sequence. So the divide by 3 counter is observed on this digital test board. Now the fifth part of this experiment is to design a divide by 4 synchronous down counter. Again, the counter is a synchronous one, hence the clock or the will have a single clock will give a single clock to all the flip-flops. So there will be only one master clock which will drive both the flip-flops. In this divide by 4 counter will have the sequence from a higher value to a lower value. So we'll have the sequence that is 1 1 1 0 0 1 0 0 and again back to 1 1. So this pattern will keep on repeating, and that is why this is called a divide by 4 counter, since we have 4 different sequence, that is from 3 2 1 0. So we have 4 sequence number, and this pattern will keep on repeating itself, and the clock is the same for all the flip-flops, hence that is why it is called a divide by 4 synchronous counter. The design table for this divide by 4 synchronous down counter will be as follows, as it will be given in the handout. That is, from 1 1 it will move to 1 0 state, from 1 0 it will go to 0 1 state, and from 0 1 it should go to all 0 state. So depending on this output condition, the input of this of the flip-flops will be as such so that we can observe this particular sequence in a decreasing order. So for this case, we will have the MSB flip-flops input as complement of the LSB flip-flops output, and the LSB input will be all 1, that is J and K will be 1 for the LSB flip-flop. So we have designed this synchronous counter on this breadboard, and we will verify again on the digital test board, and the output will be verified using the digital 7-segment display. We will give the power supply from the power supply generator. So we can see that again we have used the IC4027 to make this counter, that is the synchronous down counter. Here we can observe that the output is decreasing, that is from 3 2 1 0 again back to 3 2 1 0. Hence this verifies our design table for this divide by 4 synchronous down counter. In this also we have since we required only 2 bits, so the first two bits of this hexadecimal display has been grounded, and the bottom 2 bits are used to connect and display the output generated by the counter. The counter is again driven by the clock. The clock is the same for both the flip-flops, and the output is observed on the 7-segment display. Hence this verifies the design of our divide by 4 synchronous down counter. So in this experiment we completed the verification of the JK flip-flop, the divide by 8 ripple down counter, divide by 8 ripple up counter, the divide by 3 synchronous up counter, and divide by 4 synchronous down counter. So with this we complete the 8th experiment of this course. Thank you.